So, going to be talking about addressing the transaction challenge and really delving into why this is such a challenge in cloud native. As it's already been said, my name is Grace Jansen. I'm a developer at IBM. If you can't tell from the accent, I'm based in the UK. And if you guys have any questions that I don't get around to answering today, feel free to contact me on Twitter. My handle's there. It's at GraceJansen27. Feel free to ask questions or just if you want to connect and learn more about this space. So without further ado, I'll get started with this. So why do we care about these sorts of things specifically for cloud native applications? And that's often, hopefully you guys have seen Toy Story. I'm a big Disney and cartoon fan, so you'll see this repeated throughout my presentations. But we get so excited with the cloud. You know, we think of it and we go, ooh, the cloud. We think of all these benefits that come with it, like agility, flexibility, cost reduction, scalability, dynamic scaling. And we want to be able to achieve those characteristics for our applications. And one methodology that's often quoted for this is things like the 12-factor application methodology, which really lays out key aspects of your application that you should be following or considering if you're trying to achieve these characteristics. Well, when we start to look at methodologies like this, we start to notice sentence like treat backing services as attached resources, or for example, execute the app as one or more stateless processes. And so it's these kind of comments and sort of reiterations within methodology like this that sort of lead to this understanding of, oh, cloud native must mean that we have to be stateless and have stateless microservices when we're designing applications if we want to achieve these characteristics and make real use of that cloud infrastructure. But is this really the case? Does it have to be stateless microservices that we're using? And this is what we're going to examine today in this session. So the first thing we need to consider if we're going to be looking at whether we can use stateless or stateful and how to be cloud native is what's the difference? So let's take a look at what do we mean by stateless and what do we mean by stateful? And for this, I'm returning to cartoons. Again, hopefully you guys have seen Finding Nemo. If you haven't, please take that away as some homework. It is a fabulous film, amazing animation, and most importantly, fantastic characters for us to use to explain stateless and stateful. So we've got Marlin on the left, who has a brilliant memory, and we have Dory on the right, who isn't so good at remembering. And that's kind of the premise of this film. So in this, we can see that actually Dory is a really great example of something or someone who's a little bit stateless. She's very happy-go-lucky. She doesn't really remember that much about previous experience. And so when she sees events happening in front of her, she can respond very quickly because she just responds on a whim. She doesn't really consider the consequences of what her actions will do. When she sees a jellyfish, she jumps on the jellyfish. She's not really thinking about the fact that she might get stung. And she's also very forgetful as well. Whereas Marlin, on the other hand, really sort of represents a more stateful form of being. You know, he always thinks before he acts. He remembers previous events from the past very well. And so he doesn't rush into anything, and he takes his time when coming to decisions or particular actions that need to be taken. So he's quite a good representation of stateful. So let's take a closer look at what these really mean, using our analogies again. So when it comes to stateless computing, really this is a communication protocol that means that we're not retaining any session information. So the state of the data doesn't get recorded between transactions. And what that really means in terms of architecture and design is that scaling the system is very easy, and recoverability from the system failure is also easier because you don't have to think about, for example, reinstantiating those microservices to have the exact same state they had before when perhaps they failed if you're bringing up a new one. So this is sort of a very quick and very agile way of developing applications, and often why people associate it with that sort of cloud native approach. However, if we move on to Marlin and think about stateful computing, this is where the state of the data does get recorded at every step across all transactions. So we're retaining all our session information. What this does mean is that scaling the system, it can be a little bit more difficult, and recoverability from system failure involves a bit more effort because you have to think about being able to reinstantiate the same state that you had before. If you're spinning up new nodes or a new pod, for example, you have to get it into the same state as the rest of your system. So we're into computing that's a little bit more complicated here. So why would we even be considering stateful computing if we want to be agile like in cloud native? Well, realistically, we live in a stateful world. When you think about a scenario involving humans instead of computers, you'll start to realize that actually it's very stateful. Imagine a scenario, for example, where we forget either a spouse or a child, one of our children, or a loved one's birthday. That's not going to go down well. We are expected as a society to intrinsically store state, dates, events, information, and so that we can easily be able to fetch that and act on that accordingly. Buying a birthday gift, for example. So it's very important for us as a society to be stateful. So it kind of makes sense that when we're designing our applications, sometimes we may need to have stateful microservices in our cloud native applications to be more realistic with what we experience in the real world. So if we're considering using stateful microservices in the cloud, how do we do this? Traditionally, we might have used something like transactions. What do I mean by transactions? So here's a brief definition of what I mean. Really, this is a group of read and write operations that only succeeds if all of the operations within it are successful. So they can impact a single record or multiple records. A really commonly used example is booking a package holiday, which can be a little tricky at the moment with COVID. But if we're looking at booking a package holiday, for example, you've got to book multiple aspects of that, and they all have to be available for you to be able to actually book the holiday. So the flight has to be available, the hotel, and if you're booking something like a taxi or a car, hire car, then that also needs to be available in order to fulfill that request of booking the holiday. So how do we go about actually doing transactions in our applications? Traditionally, we might have used something like the ACID model. And just a brief overview of what this is in case you've not come across it before. ACID is really an acronym, and what it stands for is atomic, consistent, isolated, and durable. So this is a very well-known transaction model, and it really involves very tightly coupled resources that are directed to rollbacks, and they're sort of managed by this coordinating transaction manager. The issue with this one is really, although you have things like, for example, it can be very useful if you need to be able to lock the data in order to stop anything else from being changed. However, this does mean that it is resource locking, and there are issues associated with that. So really what these keywords mean is that in order for the changes to the data to be performed, they either all have to be performed or none, all at the same time. Data has to be in a consistent state before and after the transaction. No other processes can change that data. This is where it comes into the resource locking while that transaction is running. And the changes made by a transaction must persist. They can't just be thrown away. So really, this is a set of properties that you follow when creating transactions within an application. It's really designed to be used as guiding principles. The good things about it are that it does guarantee data validity, it supports data integrity and security, and in order to use it, what you'll need to use is something called a consensus protocol. So in order to basically agree that all of the operations within that transaction have occurred, you'll need some kind of consensus. There are various different consensus protocols you can use. The most commonly found really is the two-phase commit, 2PC you might see it written as. Others include three-phase commit, Paxos, Raft. There's a whole host of other ones. In my example today, I'm just going to show a two-phase commit just to keep it simple, and also because it's often the most commonly used. So let's take a look at what would happen in a traditional ACID transaction, for example. So we're going to use that package holiday request as our example. And in this, we have our holiday request coming in. We've got the two-phase commit coordinator there. So that's getting the consensus. And then we've got the various different microservices here controlling each of those various resources. The plane ticket, the hotel reservation, and the car hire reservation. So the first stage we're going to have is phase one, which is really sending out the information about sort of the fact that we want to potentially book this holiday. So what's going to happen is we're going to send that request, and that request is going to be sent to the coordinator. The coordinator will then lock the resources. So remembering back to those characteristics, so nothing else can change the data whilst we are making a change to that data. This is where that resource locking comes into play. So once they've been locked, they'll then respond to the coordinator, and that's the end of phase 1. All fairly simple so far. Let's take a look at phase 2. Now, there are various different scenarios I'm going to show you here. The first scenario is, okay, what happens in an ideal world where we have no issues, this is probably pre-COVID, no issues with booking a flight or booking a hotel or booking a car or whatever. So let's take a look at our ideal scenario. So in this, we can say, we are prepared and ready to make that reservation. We have tickets available for everything, for the flight, for the hotel, and for the taxi, so we're all good to go. The coordinator will then send a commit message back to those microservices. The microservices will then commit those resources to this particular customer for this transaction. They'll confirm that back to the coordinator, and then the coordinator is able to send that confirmation on, and money is then taken for that transaction. This, in an ideal world, works really well. But what happens in potentially the more likely scenario, especially at the moment, where at least one of those resources isn't available? So let's take a look at scenario 2. Now, in this scenario, we're going to say the flight is unavailable, which is happening more and more at the moment. So in this, our flight microservice sends back a request that says, actually, I'm afraid all the flights are booked that you could take for this package holiday, so I'm actually not available. And so instead, what the coordinator says is, abort, we can't do the transaction, because if all of you aren't available, I can't do this transaction. So they're going to abort that, they're going to become unlocked, and we're going to send a failure message back to that holiday request to let them know, or no payment will be taken. Now, there are various different issues with using this kind of transaction, especially for cloud native. So the first thing is, it's pretty slow. The fact that you have to wait for all services have to wait until the slowest service has finished its confirmation to be able to proceed. So the overall performance of the transaction is really limited by the slowest service. The two-phase commit protocol is slow by design because you have to have so much communication going on and dependency on things like the coordinator. So it can lead to scalability and performance issues in things like microservice-based architecture, especially when you're involving multiple services. It's also important to note that two-phase commit protocol is not supported in NoSQL databases. So if you have a microservice architecture where you've got one or more services using NoSQL databases, a two-phase commit can't be applied, so you can't even use that. And there's various other ones. In fact, one of the biggest ones actually is communication failures, especially in a distributed environment like cloud native. The fact that you're now reliant on network communication between microservices. Well, what happens when this goes wrong? Let's say suddenly we're unable to communicate, or our microservices go down for any particular reason. We're now reliant on being able to communicate with them. So, did they already send their response? Are they aware that the coordinators already sent them a request? Did they respond in time before they failed? What happens if they didn't? Have we put in failure, sort of rollback behavior for that? You've also got the issue of that coordinator in the middle. The whole onus of the transaction is on the coordinator node, and that can become a very big single point of failure. If that were to go down, then essentially, where do you store the information of the current status of that particular transaction? What happens when you need to bring up a new coordinator? How do you reinstantiate that state if it's stored elsewhere? How do you get it back into basically what happens to that whole transaction? In fact, you have the potential of taking an awfully long time potentially for that coordinator to come back up, and in which time the resources are still locked and nobody else can make a flight or a hotel or a taxi reservation. So now you've got a system where you've locked not just your own transaction, but you're also affecting a bunch of other transactions that are trying to occur at the same time because you're still waiting for that coordinator to come back up. So when we're talking about a distributed environment, where often we have potential communication failures, microservices that might not be responding, and you've got this resource locking. There are some very potentially big failures that can occur if you're using something like an ACID model. So that's where we might potentially turn our attention to something like a Saga pattern, which is a potential alternative to use, especially when we're looking at doing transactions in a cloud native manner. So what is the Saga pattern? So the Saga pattern is a little bit different to ACID, and I'll show you the sort of acronym for this in a minute. So this is really a failure management pattern that helps to establish consistency, particularly for distributed applications. It again acts as that sort of coordination role. So it helps to coordinate transactions between multiple microservices and is really designed to help you maintain that data consistency. It's a sequence of local transactions where each transaction updates data within a single service. So the main principle is the same, it just goes about it in a slightly different way. So the nice thing about Saga, especially for a distributed transaction where we might have communication failures or microservices that aren't available, is that actually it usually performs better in this distributed environment because it doesn't require all of the services to be available at the same time. It is what we'd call eventually consistent, which I'll get onto now. So the Saga pattern is actually based on an acronym called BASE. So it is slightly different to the ACID acronym that we were looking at earlier. So instead of having this really strong consistency and isolation, that's where that resource locking comes in, instead we have a much softer state and we have this eventual consistency. So it's not always consistent all the time, but eventually it will be consistent with the state of the system. So we have basic availability, soft state, and eventual consistency. That's the main principles that Saga sort of uses as its guidelines. And what this means is that we're sort of, if you look at the CAP theorem, we're more aligned with something like an AP system. So if you've not come across the CAP theorem before, it's a great theorem that helps us to really bear in mind that our applications can't be all of these three things strictly all at the same time. And so it's about prioritizing, depending on your particular application and your particular use case, which of these characteristics you need to be most strong in your application. So in this particular case, as I mentioned, we are prioritizing our partition tolerance and availability. And so what that means is that we have to be eventually consistent instead of strictly consistent. So that's why we kind of fall within this part of this Venn diagram. You can check out more about the CAP theorem online. There are loads of different articles that explain this in more detail. But just to give people who are aware a sort of sense of where we are within this. So now that we've sort of had a look at what the Saga pattern is, let's take a look at how that can affect the various scenarios that I showed. So scenario one, in our ideal world, we have all our resources available again. So in this one, what we're going to do is this time, we're going to send our requests directly to the microservices. So in this case, we're going to send our request to the taxi service first. That confirms that it's able to have a resource for us, and we then essentially reserve our money for that particular transaction, for that particular operation. We then are in an inconsistent state. So this is really where we get into that eventual consistency, because if the flight or the hotel wasn't available, well, we've already reserved that resource in the taxi or the car microservice. So we are in an inconsistent state here, and that's something to bear in mind. Next, we'll send a request to the hotel booking service. Luckily, we're in our ideal scenario, so all of these are available, all of them go through. We get a confirmation from that last microservice, and we know that our transaction has been successful and our state is consistent. What happens, however, when we have at least one resource not available? I'm going to skip the first few steps because you guys get the idea. So in this, we've essentially already gone to the car microservice, the hotel microservice, and those resources have been assigned to this particular customer. However, as is the case often, we are unable to book our flight. So when we send our request to our flight, actually there aren't any tickets left. So instead, what happens is in this particular pattern, instead of a rollback, we have something called compensating actions. So a compensating action is triggered to then cancel the other sort of items or operations that were part of that transaction, and essentially it create compensating actions for those to make sure that they aren't reserved for that customer anymore, because they can't all be reserved, and so the transaction can't be successful. And then essentially a message will be sent back to let that customer know. So this is the difference here between Saga. Another difference between Saga and Acid is, instead of having rollbacks, this is more of a forward strategy rather than going backwards on ourselves. We never reverse what we've done. We just do another action that happens to reverse what we've done, if that's what you want the compensating action to be. So this is all about compensation. Now, hopefully this diagram sort of shows you the fact that the items in blue are the original actions, and the items that are in yellow are those compensating actions that we then enact if we need to, if our transaction fails. There are two ways of coordinating sagas, and this coordination approach depends on sort of what implementation you're using, as an example. So we can either use choreography or orchestration. So the first approach I mentioned was choreography. Now in this one, there is no central orchestrator. So each service participating in the Saga performs their transaction and publishes events. The other services then act upon those events and perform their transactions. They also may or may not publish other events based on the situation and their particular sort of programming. So this is kind of the example I just showed you, where we were sending those requests directly to the microservices. So each microservice here is part of the transaction and publishes events for the next microservice to act on. The second approach, and this is one that I have in one of the demo apps that I'm going to show, is orchestration. So in orchestration, you do have a single orchestrator that manages all the transactions and directs services to execute local transactions. So this really acts as that central controller of all of the local sort of transactions that are part of the overall transaction, and it helps to maintain the status of whether that transaction is complete or not. So in this, it will essentially, the original request will come directly to the coordinator and then be sent to the individual microservices. Now that we've taken a look at Saga, I'm going to go into how you can actually make use of this with open source technologies. And one of those is MicroProfile, which actually uses the orchestration coordination technique that I was just going through. So hopefully you guys have come across MicroProfile before. If you've not, it is a fantastic open source sort of specification that's really designed by the community. And it is all open source, and it's essentially designed for developers who are using enterprise Java or Jakarta EE for their applications, to enable them to make microservice-based cloud-native applications. So this specification offers a bunch of different APIs. The bottom pyramid sort of triangle shape you can see here, they're the APIs that come as standard as part of the MicroProfile stack. The latest one that's out at the moment, I believe, is 5 point something, but I just wanted to show you this diagram to show you roughly what the most up-to-date versions of those APIs are. The sort of sideways L shape that you see in the top right here is some of the standalone projects that are still worked on by the MicroProfile community, but aren't yet part of that standard stack. It's hoped that in future they will become part of it. And the one that we're interested in, actually, for sort of doing transactions in a cloud native manner, using things like the Saga pattern, is MicroProfile LRA. Now, LRA stands for Long Running Actions, and that's what we're going to go into next. If you're interested in finding out more about MicroProfile, there's a link here that takes you to a whole series we've made on what MicroProfile is, and you can find out more about it there. So, MicroProfile Long Running Actions. What is this? So this is really a loosely coupled transaction model designed specifically for cloud-native microservices. It is based on that Saga pattern, so you can start to see all these things coming together, and it relaxes those constraints of ACID transactions, so more aligned with those base transactions. Essentially, it is a long-running orchestrated activity, so a cloud-native transaction. The goals of sort of creating this API was really to enable there to be no strong coupling between services, and to simplify application error handling when multiple services needed to be part of a single transaction. And it also allows actions to finish early and ensures the execution of application-provided compensating actions. So remember that forward strategy rather than using rollbacks. So really embracing those characteristics of Saga. So how do we make use of MicroProfile LRA? Well, MicroProfile is a specification, so you'll need an implementation to be able to actually make use of it. There are lots of different implementations from various different vendors who contribute to MicroProfile. The one I'm going to show today is open source project OpenLiberty. So we have a demo app that you can check out if you're interested in finding out more about this. So in OpenLiberty, you can make use of MicroProfile LRA. And in this particular one, we're using that coordinator approach. So we have two parts to using LRA in an OpenLiberty application. We've got the LRA participants and the LRA coordinator. One thing to note is OpenLiberty uses the Narayana implementation of the LRA specification. There are others that you can make use of if you want to. So let's take a look at what kind of code we need to be adding to our applications in order to have microservices that are participants in a transaction using LRA, and also to have that LRA coordinator to manage all of the various aspects of that cloud native transaction. So the LRA coordinator will probably look a little bit like this if you're implementing it in OpenLiberty. And within this, you'll start to, you can also see this, by the way, at the link at the bottom here. That link is in all of the pages that are relating to this demo. It's on GitHub, it's all open source. So if you go in and find something wrong with it, for example, feel free to add an issue or suggest improvements if you see anything. So this is the kind of thing that you'll need for the LRA coordinator, and you can see the feature added there to it, MicroProfile LRA coordinator 1.0, and just some sort of configuration for it. Now, when it comes to the the participants, you'll need to use some annotations. This is very common within the MicroProfile specification, as it's essentially a lot of the APIs that are used in MicroProfile use annotations. So these are kind of the most basic annotations that you'll need just to make a very simple participant joining your LRA transaction. So you'll need these three annotations, but there are additionals you can add on top. So @LRA is the first one you'll need. This allows you to either join or create an LRA method that then handles any required business logic. You've got the @complete. As the name suggests, this is essentially what happens when your transaction is complete. So it gets called after the LRA completes successfully. And again, it handles any required business logic that you might need to put in place for that particular microservice. Then we've got the @compensate. And again, as the name suggests, this is where your compensating action comes in. So this is going to be used if the LRA fails for any reason. And again, includes any logic that's needed to revert any changes that were made in that original join or create method. So it's going to look a little bit like this. So you can see I've had to kind of chop screenshots of the class to fit this on my slide, but you can visit the whole class by heading to that link and heading to one of the LRA participants. So you can start to see we're using the @LRA annotation here to join or create an LRA. We've got the @complete and some business logic of what we need to do when it completes, and the @compensate, again, just some business logic of what we need to do if the LRA were to fail. As I mentioned, there are additional annotations that you can make use of. So we did the @LRA, compensate, and complete. You can also do annotations like @forget. So that indicates that you might need to release a resource that was allocated for this LRA for a particular reason. @leave, so if your class isn't supposed to be part of that LRA anymore, or @status. So it's invoked if you should report the status of that particular microservice. So you can use those additional annotations as well. But really, it's fairly easy to add it into your application just by using those three annotations to be able to add microservices into a particular transaction, for example. As I mentioned, you can check out this demo using this link here if you want to. It kind of follows the same model that I was showing throughout the presentation. It is a holiday booking system, so it should be familiar in terms of the architecture and how the application is behaving. So please do go check that out if you're interested in finding out how we've integrated LRA into this and to try it out for yourself. So to summarize, hopefully what I've shown you is that stateful microservices are still needed in this cloud native world. And unfortunately, traditional transactions based on things like ACID principles aren't really suited for cloud native. But there are alternatives like Saga and implementations of that pattern like MicroProfile LRA that can help to provide really effective and suitable cloud native transactions for microservices. And the great thing about them is that they are all open source tools and technologies, so you should be able to try them out for yourself if you're interested. Some useful resources, in case I haven't given you enough in the presentation so far. If you want to find out about that beta, which is essentially where you can find out how you can use OpenLiberty in our most recent beta, or if you want to use the demo itself, then you can check out that on the second link there. I've also included some to specific resources like MicroProfile LRA spec, if you want to go into that in more detail, or into things like what's a Saga, and going into Saga in more detail as well. Some links, for example, to MicroProfile and OpenLiberty, in case you're not familiar with them and you'd like to get started. They are fantastic open source projects, so please do check those out if you're interested and want to have a go yourself. Thanks very much for listening. Hopefully, I've entertained you with some cartoons and interesting information about how we can potentially do transactions in a cloud-native manner. Thanks very much.
Grace, I'm sure that everyone liked it. Thank you. And we have just a couple of questions before you go.
Yeah.
What if during the commit phase our stage connection is broken and we can't store the state? How coordinator and other services will react?
So yeah, this is the whole thing around. That's why things like an ACID transaction can be an issue, right? Because if you're in a state where you've locked that resource and suddenly either the communication is lost or your microservice goes down, how do you know whether the coordinator received that? Where is that state stored? When you reinstantiate that microservice, how do you know that it's going to know that it sent that or not, that the resource is locked or not? So it can be complicated when it comes to using. That's why the traditional transactions might not suit that well. But by using things like Saga transactions, we can be a lot more flexible in that, because we're in this sort of inconsistent state because we've not locked our resources. We haven't prevented other transactions from occurring, as an example. And we can also use things like, for example, at status. So our coordinator can use that annotation to be able to say, okay, now that you've come back up, what's your status? Like, have you reserved a resource for me? Do you think you've sent me a communication because I haven't received one? Could you send it again? So we can start to add in these sort of actions that enable us to have behaviors to negate the potential for us losing a communication or losing a microservice. And so that's where really these specifications have been designed with that in mind, that the cloud does fail and that stuff doesn't go quite to plan. So we need to be able to behave in accordance with that.
Cool, thank you. And oh my God, so many questions.
Oh, wow.
Okay.
People have paid attention. Thank you.
Okay. Great. Just really great talk again. Thanks, Grace. And why Stateful is needed? I can store the Saga info in database, right?
Right. So it depends on, like, if you were to store it in a database, for example, and it depends on your application, right? Because not all applications need stateless. Just like I would argue not all applications need state. Just like not all applications need to be microservices. Like, it's completely dependent on your particular use case and your particular application. It might be the case that an external database wouldn't be applicable because you need, I don't know, I'm trying to think of one. For example, with the holiday transactions, you'd have to update each database individually, and then someone would have to keep track somewhere in maybe a separate database of whether those databases have been updated for each of those microservices based on their availability, and have you reserved it? And then we get into the locking issue again, and like, it gets complicated, and this is a complicated topic. I'm not saying it's easy, and I'm not saying I've got the exact answer you need. I'm just saying it's something to consider, that sometimes some applications might need to have state in a cloud native way, and that this might be a potential scenario you'd want to use stuff like Saga for. I would say I'm going to take the consultancy answer here and say it absolutely depends on your application.
Thank you very much. And I think it would be the last question for you. It's which approach gives better performance, ACID or Saga?
Oh, again, this depends on what you need it for. So if you are using one service, or even maybe just two services that are part of this transaction, and you're not really bothered if that transaction were to go wrong, you don't really mind too much, but you definitely want to make sure that if your transaction is editing it, nobody else does. If that's the case, the use case, then Acid would probably be the better thing for you to use. But however, if you care more about consistency, Acid. If you care more about availability, you're looking at Saga. Um, that's the cap theorem trade-off that I'm talking about. And in terms of Saga, you're then looking at, okay, I do care if my microservices go down. I want to be able to continue the transaction. I don't want to lose the transaction at all, but I equally don't mind if I'm in a slightly inconsistent state. So it completely depends on your application. As I said, I'm not saying Saga is the way to go. It just might be the way to go. Consider it. So really, it depends on your application and your use case.
Good. Thank you very much, Grace. It was a really nice presentation and cool speech. Thank you for joining us today and thank you for supporting Ukraine.
Thank you so much. Great
Goodbye.
to join you. Bye bye.